Thank you, Santosh. Can everyone hear me? This is small, so I know it's still early in the morning. Hopefully you had your coffee. And I'm obviously very happy to be here. Santosh and I studied together, and we go all the way till 2002, I think. So yeah, I'm very happy to be here. This is my first time visiting AI2. I've been in Seattle, and I'm obviously surprised with the weather. So I'm going to take part of the credit, saying that I brought the sunshine with me from California. So yeah, today I was thinking about how to present this, and there are two ways I was going to do it. One, the first half an hour, I was going to go breadth, where everybody here kind of gets a sense of what kind of problems we are working on at Facebook in computer vision. And the second part, more near and dear to me, which is how do we do representation learning when the task is not very well defined. And this is one of the challenges that we face at Facebook, because every time we venture on a new adventure, there's a new task related to computer vision that falls in our lap. So that's basically the outline. I want to, since it's AI2, and I want to start with AI as the first slide, and then we'll go to computer vision, which is like the small part in AI. So why do we care about AI? Why is AI important to us? So if you think about Facebook and what people use Facebook as, it's basically a communication platform. So one of the fundamental things that we need to do is understand the content and understand users and connect the two very well. So AI is important in that sense, and this is the mission for Facebook AI research. And I also want to start off with this being described in much better words and more concretely by Jan LeCun, who is the director of Facebook AI Research. So let's start with what he thinks we want to do here.
Our goal is to build intelligent machines to help people in their daily lives. What makes us intelligent is our ability to learn. And this is what we're trying to reproduce in machines. To some extent, we get inspiration from biology. What we can do with current technology is build networks of simulated neurons on the order of magnitude of the brain of a mouse, let's say. So the way we train our machine, we show a bunch of images of, say, breeds of dogs, and for each image, we tell it what it is.
We want the machine to be able to learn to perform the tasks. The more we show them examples, the better they get.
And what's very interesting is that after a while, it can do this with a new dog it's never seen before. It's able to exhibit superhuman performance on a particular task. So how can we help people's life with this?
So yeah, not sure what happened there, but basically, we'll see the later part of the video, I guess. How can we help people's life with this? That's where the next things come in picture. So the first one is machine learning. So the first component of AI in general right now is machine learning, and specifically deep learning. Second is understanding language. Probably based on my conversation with Mohammed and Santosh, I think these are very relevant to how AI2 internally is also organized, which is good. It gives more reinforcement. And finally, it's perception. It's perceiving the world. Which is understanding speech, understanding images, videos, basically vision. And if you think about what all of these will amount to, it's basically building new experiences and new connectivity platforms for people to communicate better and in a more richer way. So these are various components in our AI group and how we think about solving AI or getting towards building intelligent machines. So with respect to going a bit deeper, I want to now start getting into the computer vision aspects of things. There are three big goals for my group. One is unlock information, and I specifically left out unlock information from what, because in 2012 when I started working at Facebook, it was predominantly images, but as our platform evolved, it's now video first. Number of videos uploaded on Facebook is extremely, it's growing crazy. So now I need to understand videos. So we want to unlock information from various media types. So it's photos, videos, and new types of data that you'll see. Obviously, all of us here are, when we are doing research in computer vision, we want to deepen our understanding. And in a bit, I'll tell you what that means. And finally, at the end of the day, we don't want to keep annotating millions and billions of content. You want to reduce the amount of supervision to train these models. So we will be, most of my group's efforts are pushing pushing our efforts in pushing these things in all these three dimensions. So with respect to unlock information from visual content, Facebook's data is a stream of data. It is not going to be an ImageNet, or it's not going to be another data set. It's every 6 minutes we have an ImageNet. So this is a stream of photos that get classified with the existing models. And that's not, the distribution of this data set keeps changing, keeps evolving. When we have more users coming from India, the kind of distribution is different. So, and we have 1.7 billion people and over 2 billion photos every day. So the distribution of photos in 2012 was completely different to the distribution of photos right now, and will be different in the next few months. So think of all the algorithms that we need to build, and with each group, when we acquire Instagram, suddenly we have a new kind of data set. There are filters on the images and so on and so forth. So that's one modality. And then there is videos. As I said, we have videos ranging from 2 seconds to 2 hours, and you cannot use the same algorithm or same kind of techniques for all these kinds of modalities and for various things. So there are also 360 videos that we support, and 360 photos. So the kind of algorithms you need to build are very diverse when you have to handle this kind of data. And finally, we have connectivity efforts where we are using LiDAR data to understand the world and understand the furniture in the world. They call it furniture. Basically, it's electric poles and infrastructure, so that we can use our hardware, the Facebook custom routers and Wi-Fi connectivity devices installed in these places to provide free connectivity. So the computer vision team now needs to handle all of these modalities for all of these various tasks. That's the first challenge. The second challenge is, in the beginning, you just want to know what is in the image, so we all know what that problem is. It's classification. But then we now have models that are working really well. I know we have a bunch in YOLO and other things in AI2 as well, which is around detection. So you draw a bounding box around objects. Then you get into the segmentation, which is pixel-wise labels, and semantic segmentation, which is also cardinality of how this pixel belongs to this particular sheep and so on. So I stopped here because we know these are the problems that we have been working on for a while. But think of these axes as you need to understand, get more and more understanding as the complexity of problems and the kind of experiences that you need to build start increasing over time. So that's another challenge. The third one is level of supervision. So of course, the best models today are trained on data that have been fully supervised. So you take millions of such examples and show that it's a cat. But what the kind of content that Facebook has is interesting, because you can now start thinking about weakly supervised. So for every photo or video, you know who the person is that uploaded that photo or interacted with that photo. You have text around it. Very noisy, of course. So how can you use this information to build better models? That's an open question, and we have a bunch of work in this domain. And finally, so it started off as a mouse. That's Mark's dog, Beast. And it can be confused as a mop or a sheep or a dog. So the reason I put that video there is if you actually look at how the video started, it looks like a mop, right? So the idea here is you have millions and billions of these videos that are being seen by this algorithm, and then you learn visual representations of the world. That's completely unsupervised. So that's again, if you look at from left to right, it's level of difficulty, but and less level of supervision. So this is another challenge that we want to solve. So put all of this together, that's my group. That's essentially what we're trying to do at Facebook in terms of efforts. So currently, as you all know, the best things that work, the best models that work are fully supervised. So the models that we have running that is used by the Facebook website and Instagram and many other teams at Facebook are fully supervised. So this is not new to anybody here, so I'm just going to skim through this. It's millions of annotations, various examples, deep neural network with many neurons, and you have a large-scale deployment. So that's what is running right now. Obviously, we want to decrease the number of annotations. Yes, go ahead. It depends on the task, actually. So to learn the best feature, it's fully supervised. But to learn the feature for a specific task on top of these visual embeddings, it's actually weakly supervised. So that's the interesting challenge that we are trying to solve. And I'll get to that in a bit. Basically, the answer is it's a mix. So there is no ratio and proportion. Depending on the task at hand and how much annotations we have or how much supervision we have, we basically go fully supervised in some tasks, and in some tasks it's very weakly supervised. I want to quickly go through some applications in scale. Some might be obvious, some are actually not so obvious when we built it. So one of the things that we just saw is this stream of photos. So every photo actually gets classified into thousands of concepts, and that information is available as part of Facebook Graph. And then any team in the company can actually use the metadata in that graph and build whatever experience they want. Which this is the way we designed it, because then you have this universal vision model that's actually crunching through all of this data, photos and videos, and then making the metadata available. How is it useful? So one of the applications that I cut short the video, I just realized. This is basically the extension of that video. So this is actually called automatic alt text. And for all of us who work in computer vision, it's actually a very simple thing, image classification. But how is this useful at Facebook? So you can just take a look.
Wonder what it's like to use Facebook if you are not able to see? Turn on your sound to experience it. Screen readers, like this one, read aloud what's on the screen, making Facebook accessible to the millions of people worldwide who can't see. And now Facebook's new technology can tell them what's in the photo. Facebook, search. What's on your mind? Xiaomi Wu, March 6 at 10:14 p.m., with my college buddies in my favorite place, ready for a great weekend. Photo, image may contain, tree, sky, outdoor. Demetric Sanders and 7 others reacted. Manohar Pulari, March 6 at 7:48 p.m., Sunday night splurge. Photo, image may contain, pizza food. UN 17 others reacted, 13 comments, 2 shares. Peter Cuddle, March 6 at 4:22 p.m., we finally made it. Photo, image may contain, 2 people, smiling, sunglasses, sky, outdoor, water. Asked Ivawal and 29 others reacted. Facebook's mission is to connect the world. And that goes for everyone.
So this is the automatic alt text feature that was released. If you think about the model, it's actually a classification model. But think about the challenges that we had to deal with before we deployed this. If you get a person classified as an animal, Facebook is going to be in the news every day. So the amount of challenge that we had to deal with in shipping a computer vision model that we all know works really, really well in terms of classification is itself very challenging. I just want you to wrap your head around that. But after we released it in March, we have had only positive press, and there are millions of people who are now using this. And it's been amazing. In terms of the core technology, it's very simple, but making it work at scale, even a 99% accurate system, when you apply it on 2 billion images, there are 20 million images that get wrong. So something to keep in mind. So obviously we have technology beyond classification. So this is the deep mask stuff that we participated in COCO segmentation competition, and this gives you segmentation. Now this is paving the way for the next experience, which you'll see in a bit. So here, basically the same visually impaired people can actually now interact with the photo. It's called talking images.
Snow, snow, person 1, tree 1, person 1. Lake, person 2, person 3, person 4, tree 2, snow, person 4, skis.
So you get the idea.
Person 4.
That's using segmentation to now give richer and richer information. Remember the level of understanding of the image, right? Then you all know the limitations of VQA. But even with the current limitations of VQA, visual question and answering, it's still very useful for a dialogue system, for a person who cannot see, to have a dialogue about the with the system. So here is an example.
Is there a baby in the photo?
Yes.
Where is the baby standing?
Bathroom.
What is the baby doing?
Brushing teeth.
So this is another example where you take it further. So all of these are prototypes, but the goal here is to keep shipping. So we'll keep increasing the accuracy, making better and better models, increasing the data set, publishing this work, and also enabling these experiences for millions of people who are using Facebook. Obviously, we are not limited to photos alone. As I said, video is growing significantly on Facebook platform. So currently, we have all the videos going through these models that gets classified in various concepts, whether it's scenes, objects, or actions. And then you have these content-based channels. And this information is then used by various groups at Facebook in the same way they use it for photos. So we actually had a work called C3D. It's basically using three-dimensional convolutions. And the idea here was to not collapse the temporal information or not fuse the information at the end, not collapse the spatial, visual information at the end. And there are a bunch of things. We'll get to that in a bit if we have time. So here is an example where we ran it on Sports 1 million dataset. This is a dataset that was made available by Stanford and Google, which has 487 different types of sports. So you can see we start with the famous sports where it's easy to distinguish and the probabilities are very high. But as we go further, you'll see fine-grained sports, which are very difficult to distinguish. So these are all the common sports. Now you get into the skating, and you have these various interesting types of skating that even I didn't know, at least when I started the project working on it. So, and then hockey and sledge hockey. People come up with a lot of creative ways to push themselves. And if you're not good with your feet, you can still play football with your hands. And finally, something you should be very careful about, mountain unicycling. So not encouraging any computer science people to do that. But OK, so the idea was simple. How do we build a good video model? And there are a bunch of work around C3D that we can get into. So this is 487 sports. These are obvious, but there were some unobvious, like not so obvious connections for us when we actually built it. So when we built our vision system, we built it such a way that anybody in the company can use it. It turned out somebody in connectivity, a physicist, basically wanted to understand. So our goal is we have various solutions to connect the world. We have something called Telegraph, where if you have a densely populated city, we use the LiDAR data and know where the furniture is and place the routers. But if we get into sparsely populated city, or actually in a developing country or complete like Africa or something, you need different kinds of solutions. You need satellites or you need drones. Aquila is our project. So you have various forms of connectivity. And we are doing a bunch of research in all of this. But turned out, one of this application could use computer vision in a very interesting way. So this is the population density map that UN and WHO basically had access to. This is the resolution, and if you zoom in a little bit, you basically, this is part of India, and this is the resolution of that the public organizations had when we started this project, when Facebook started this project. So we knew that there were millions of people here, but it's thousands of kilometers, that area. So we don't know where in this region people actually lived. So we use the same deep networks that were trained on all of these concepts, and then built models that actually could tell us from satellite imagery where the density of population. So and this is the maps that we open sourced after we processed. And the really interesting thing here is all we did was take a tile and build a simple linear classifier whether something is a building or not, and with few thousands of examples. And then we applied it billions of times on the satellite imagery that we have, and we get a heat map of what is a potential house or not. And this actually generalized pretty well across countries. So we were able to build maps like these for Egypt, for South Africa, and for Sri Lanka. And this was like, basically the technology was there, and within a week they built a model, they deployed it, and after 3 months we had high resolution maps that were 200 times higher resolution than what the public organizations had, and we open sourced it. Yes?
Do you need to recognize buildings? You could just take the pictures at night and use the light?
So there are a bunch of concerns there with respect to light, because in underdeveloped countries and places where there is not enough electricity and so on, especially in Africa, light is not necessarily the solution that generalizes that well. Yes?
You might have a similar concern that buildings don't look similar.
That's exactly the first thing as a computer vision person. I was like, this is not going to work. Don't even try it. You might have to train a model for every city or every country. And turned out that it actually generalizes pretty well. And the fine-tuning required for countries is not that much at all. So that was a big surprise for us as well. I think it's purely geometric shapes rather than the building structures. And once you have 10,000 odd examples, it worked really well.
How about the cities like Seattle? How do you think?
Thankfully, Seattle is fully developed, so we didn't have to connect Seattle that much.
How do you evaluate it? I mean, how do you know that the maps you generated are...
Yeah, it's a good question. I don't think we have a large-scale evaluation. We have some evaluation on some parts of the data, but some parts of the world, but it's not going to be a full-fledged evaluation. So We definitely evaluated with respect to some course maps that the local governments had, and there was more than 90% correlation with what maps we generated. But again, this is super limited. The idea is this is one of the fundamental problems. When you deploy a system, what is the recall for this? You can only
look at this map, and for all you know, all the black areas could be filled with houses that you're not recognizing.
Absolutely. So you just sample in an unbiased way and see what our accuracies are. There is a confirmation bias, though, that Cairo and Colombo and these capitals essentially have this denser heat maps. But it's a good question. That's one of the biggest challenges when you deploy this technology at scale, right? Okay, so there are obviously key challenges that I was trying to evaluate, but with every key challenge, there is an opportunity, and that's how I see it. So one of the things you all, if you're working in computer vision, you all must have worked with ImageNet dataset. That is the guitar dataset in ImageNet. This is the guitar dataset at Facebook. If you take an ImageNet model and apply it there, you know what will happen. So that's the challenge that we are trying to face. This is a challenge, but it's an opportunity. We can learn the visual representation of a guitar in all these challenging circumstances. That's how I see it. So that's one of the problems that we are tackling. The other thing is we don't need to see this as a computer vision problem. We need to see it as a holistic, what is the end thing that we're trying to build. So in this case, if you take all the images, for all of the images, people write a lot of text. If it's an image that's on the external website, there is text around it. So you can start thinking about joint image and word embeddings. And the nice thing is, so we did this for Flickr 100 million dataset. I don't know how many of you know about the dataset. For the dataset, each of the image has hashtags and text around it. So you can actually learn some really interesting visual descriptions, visual embeddings for words like vintage or autumn or gig. It's very difficult to say what is vintage. But again, the recall is, who knows what the recall is. But the precision is pretty cool. You can start learning visual representation for some of these very subjective things, purely without any labels, purely based on the comments and based on the text around the image. So think of this as going beyond vision now, right? It's bringing text and images together. The same thing for video. So right now, when a video gets uploaded, we actually have speech recognition running on all of the videos. So
we are on top of MBK 20. The building that is known as headquarters for Facebook. You'll find yourself looking at all wonderful kinds of flora and fauna. You can see here.
As you can see, the automatic speech recognition system does make errors. But the more important thing is, I don't think a computer vision system now can recognize B, even if you run at the dense scanning. Maybe it does, but it's limitation. But I know that there is a bee, there is a flower, or this is this location, and so on and so forth from the speech, which is synthesized from text. So basically what I'm trying to say here is to understand videos at Facebook, we don't need to see it as a computer vision problem. We actually see it as multiple modality problem, where we take the audio, put it through speech recognition, get the text, build text models, take the visual features, build, and then do joint modeling of it to get a higher level understanding that this video is about this particular topic, and this is what is happening. We have a huge push towards live video, so anybody with Facebook can actually go live using the app. So think of this way, where there are hundreds of thousands of people actually going live, and you are in your VR space. So we also have a lot of effort going on in VR. So this is an experience where all of these are actually live videos. Think of this as all of these are live videos that are happening right now in the world. And when you go and switch on the TV, you basically go to CNN or ESPN or whatever. Here, each cluster, this is visually, these are visual embeddings. The clustering is basically using the visual embeddings. So if two videos are close by, then they belong to the same topic. So you can have a food channel or a sports channel, or in the sports channel, actually baseball and ping pong or whatever. So now you explore this space as if you switched on the TV in your VR world. And then you go, you can zoom in, you can play around. And once as you see, you can zoom in and pick a particular place in this VR space, and you can pick that video and start watching that video as if you are in that channel for a bit, and then you can move to the next channel and so on and so forth. So I'll just play this for a few seconds, and then we can move on. I forget what channel we select or which video we pick in the beginning. The visual embedding here is actually using C3D, the video model that we have, and using tsne on top of that embedding. Yes, please.
So it looks like the embedding is just three-dimensional.
Yes.
It's kind of surprising that you get good clusters over the vast types of video.
So, so I don't know if you know about t-SNE. t-SNE is usually pretty good in terms of at least preserving the label, but I agree with you that in 3 dimensions, there is nothing, like you cannot get all aspects, right? So think of another content understanding kind of channels where you can select sports, and in that you get to another space and so on. So this is just the initial version of it that we built.
These videos are live videos, yeah?
So some of these are live, some of these can be offline. It could be basically, you can even have control saying, for the last 24 hours, what did I miss, kind of a way. So
the clustering for the live videos is like frame-based clustering because they're streaming.
yeah, so this is, in this particular example, this is offline, but that is the vision where we want to go to, and there will be a delay, few second delay. So that's one. I was talking to Mohammed and Santosh, and I know that there is a bunch of work here going on in trying to understand physics. So this is from work at Facebook AI Research. Rob Fergus and a bunch of folks there are trying to basically build models that predict if the blocks will fall or not from their current structure. Like in this case, and the system actually does a really good job. And this is all in simulation. They also have a bunch of blocks on the table, physical blocks, and it's really fun. So surprisingly, the system actually, the convnets do a really good job of predicting whether the blocks will fall given certain configuration. So that was very, very broad, high level of various things that are happening and some experiences that we're building, some things that we shipped, and some things that we're going to ship. I want to take a bit of a detour on representation learning and kind of things that we're working on there. I'm happy to take some questions now if you have with the content that you just saw. Good? OK, cool. OK, so there are 3 works that I want to skim through very, very quickly. So one is, this is a ICLR paper that we wrote on, let me define the problem first. So what do current models do? We basically have this big machine, whether it's a VGG model or an AlexNet or an Inception network or a ResNet, doesn't matter. On the left is all of these examples, in this particular case, a couple of dogs. And we want the model to basically predict this is class 37 or class N, right? What is the problem with this kind of approach? The problem is, what if I wanted to detect whether a dog is a black or white? Then the loss function changes. Then the representation that you have learned, is it good enough for that problem? Is it actually contradicting the original problem? That's a big question we have. And this is important to us because these loss functions, the things that we need to solve at Facebook, keep changing as we build new experiences. So the feature descriptor or the representation that I have learned for the images might actually be contradicting to the end goal that I need to have, right? So that's the problem. And distance metric learning is not new. I'm sure most of you have read this literature. The idea is you want to embed the content such that in the embedded space, the distance actually gives you some sort of a semantic notion. If 2 things are close, then they are similar. In your notion of similarity, whatever you define, if they are far, then they are dissimilar. That's distance metric learning, right? And there are many advantages of distance metric learning. You can actually do one-shot, zero-shot learning because you can embed stuff. You can visualize high-dimensional data, like images, the way we just did. You can learn embeddings and have various projections on top of these embeddings for various invariances. And you can scale to millions of classes because all you do is do a non-parametric parse and window kind of approach in the embedding and propagate the label, right? So there are many advantages of distance metric learning. And a classic, one of the first things that came out of in this literature was LMNN, large margin nearest neighbor. So you just select the margin and you push the positives closer and push the negatives farther. There is a bunch of references here. We don't need to get into that. But the problem is we are conflating 2 things when we are trying to learn representations for this particular, in this way. The 2 things are we are conflating semantic and visual similarity. So semantic is the labels that we have, which is a dog or a cat or whatever problem that you're trying to solve. And then there is a visual similarity, which is visually are they similar. So if you look at the WordNet ontology, it might be actually correct semantically, but maybe in the visual ontology, things might be different, right? So can we learn representations that try to preserve both semantic and visual similarity? That's the fundamental question that we were trying to answer, and this is basically the work in that. And local similarity was our obvious answer here. What does that mean? What that means is the neighbors basically locally are aligned semantically and visually. But overall, you don't force all the cats or all the dogs to be together. Let's get to that in detail, basically. Sorry, I'm going to skip that. Yeah. So local separation instead of global separation. Instead of forcing all cats to be together, all dogs to be together, we basically learn the representation space such that locally there are a bunch of cats, and they could have visual similarity and semantic similarity. And then there might be another cluster of cats that could be visually completely dissimilar to this cluster. So you give this flexibility, and you learn the representation. So the standard distance metric learning is trying to force everything which is semantic in nature together, whereas our version, which is the magnet loss, basically gives you this multiple clusters where if they are visually similar, they can still be closer, but semantically there is an inherent cluster locally. So that's how do you train this? And what is the intuition behind this? Now we have this nice clusters where black dogs and black cats are together, but in that space there is also all the black dogs are together and all the black cats are together, and so on and so forth. Intuitively, the representation that actually gives you this should be able to generalize much better than the representation that we learn if you just preserve the semantic label. Hopefully that is something that you all buy into. So that's the more higher level point here. It's like when we try to learn representation that preserves these two things, the intuition here is that representation will generalize to various other tasks, and that's the goal, and we show that in this work. And so previously, if you ever trained a triplet loss, if you ever used triplet loss and trained a network, what you do is you have a query, and you have a positive, and you have a negative. You basically forward prop through the network, and you back prop such that the distance from the query to the positive is smaller and the distance from the query to the negative is farther. And you do this many, many times, and you train the network using back propagation. And after triplet loss, after that mini batch, or after that one particular forward prop, you get a much better thing. But what magnet loss does is you have a sense of this cluster representation. So there are two advantages that you get. You basically bring clusters together and push clusters away. So you don't, and if you have ever trained a triplet loss network, you know hard negative mining is extremely hard. Like it's one of the most important things that you need to do to get the network to train well. So you need to do hard negative mining, and then there is this margin. Yes.
It seems more natural to me if you have black versus white and dog versus cat. I think of those as like orthogonal dimensions.
Yes.
What's the motivation for thinking of them as like different clusters as opposed to orthogonal dimensions?
So if you were to basically if you train a network where you just preserve cats and dogs, and then for some reason you need to now start your network, or the feature is required to predict if something is black cat or black dog, a new attribute. How would you do it? That representation is not going to get you the same accuracy as this one. So the problem here is there are new loss functions and new tasks that keep coming up, and you cannot relearn the representation for that task. Then how do you learn the representation? That's the problem setting.
Well, you could say you could just be learning orthogonal dimensions, something like singular value decomposition.
Yeah. So disentangled embeddings, or I forget the exact word, Honglock, basically, essentially, there is some work in that. This is another kind of work. And think of this as just one dimension. There could be another dimension, which is pose. Like you now start respecting the pose as well. And inherently, when you do this, when you give this flexibility to the loss function, you see that the clusters learned are homogeneous in some particular attribute, whether it's pose, or whether it's material type, or color, and so on and so forth. So that you are inherently learning these things without having to annotate them. And that's what we'll show. That's the advantage. I sense that I didn't answer your question.
I still think the basic intuition seems a lot like singular value decomposition, and I don't see, like, I don't quite grasp sort of the trade-offs between doing this approach versus using thinking of it as like orthogonal dimension.
But even if you, so let's take the example of you do SVD on the representation, okay? But to do SVD, if you do SVD blindly and then you still have to annotate, right, that this is black dog or this is, in this principal component is for this pose and so on and so forth. If, so maybe we can talk a little bit more. I'm curious to hear. I understand what you're trying to say, but I think this is learning this way end to end will give you a more general representation. That's my sense.
So, are you like the new categories or like being black is important? That may happen later after like you have like the category classification. Now after 1 year, now you decide in Facebook to have like now we want to separate it from black dog or black cats, and now there's a new category, and this is the reason that you care about this, because otherwise you could have that as a category at the beginning.
Yeah. So that's exactly the point. Today we will have a loss, like we have, let's say, 10 loss functions, and each one has this 100 concepts, and the other one has some other 1,000 concepts. But tomorrow there's this 11th loss function that comes, and then you want to, what are our options? We can fine tune the network, in which case we change the representation for everybody, or we basically use the representation as is and train another network on top, which is more expensive, or the fundamental representation that you have itself is generic and preserves certain things that will be useful for various loss functions. So that's basically where we are going. And you will see why this is important in the results. So we think of this as an EM-like algorithm where you don't know the clusters and you don't know the representation. So you're iterating on both, basically. Without, and the nice thing is, since you have this sense of clusters, you can actually do hard negative mining. But more importantly, that the first bird is actually a different class than all these birds. You are in the normal loss function, in the softmax, you're forcing them to be separate blindly, right? But they're visually so similar. So your representation is trying to overfit to these semantic labels and not respect the visual similarity. That's at least the intuition, and so on for Shark. So I'll skip this. It's in the paper. There are few experiments that we did where we literally took the embedding and applied it on various problems. So the ones that are that everyone know here, hopefully, is Stanford dogs, the pet dataset, and the flowers, which is more fine-grained. And you can see that the magnet loss gives much better error on all of these datasets, but these are much smaller. The more important question that we wanted to answer was, if I take this representation, can I now apply it on a new problem? So I don't know how many of you know ImageNet attributes dataset. So you basically have 30 attributes, I think, for a subset of ImageNet. So what we did is we took, so this magnet loss was used on the network to train for purely semantic labels, right? Whether something is a cat or a dog or a cheetah. But we took that representation and did nearest neighbors and predicted attributes. And you can see the magnet loss across various neighborhood sizes significantly outperforms both the triplet loss and the softmax, which is essentially what we want. So inherently, we wanted it to put all the spotted things together, all the furry things together, and so on, without using the label spotted, without using the label furry. That's at least one way to test the generalization. Another way is, these are just curves. Another way is to, again, do t-SNE on the magnet, and these are the white dots are the clusters. And you can actually see some clusters from two different classes together. So this is sharks in the deep, manta rays in the deep. But manta rays with people is actually farther from manta rays in some other place. Go ahead.
So the clusters are basically based on appearance, or like, can
so
I have it like pose-based? Like, I want poselets, I want like all the right-facing.
Yeah, but then if you use poselets, you might have to use poselet as a supervision signal.
Basically, the clustering is appearance, right?
Clustering in this sense could be appearance, could be anything, right? It doesn't matter.
But if I want clusters based on pose,
then you need ground truth. Then you need to provide pose as a supervision.
Then it's basically appearance.
It's sometimes actually, so it's a combination of things. It's appearance, material, things like sharks, and like there's another one like manta rays with people and manta rays in the deep. It's not appearance. Like there is a person plus manta ray. It's a class. I know what you are. Yeah, definitely.
This was there even in like deformable
DPMs.
They used to do latent subcategories.
Yes.
It used to get something like this.
Yes. So here we are giving that flexibility as on the fly. If manta rays with, I don't want to define manta rays with people as a class. If manta rays with people is a thing, then it will be a thing and it'll emerge as a cluster. We want that to be learned from purely data. And the label that we get is manta ray. You can actually investigate further and further on this on these embeddings, and you see that there is impalas with people and impalas that are different, and so on and so forth. I mean, all these details, higher resolution visualizations are in the paper, so I don't want to even get it.
So
yeah.
with people, that label, you added it, or the?
No, we identified, like we actually didn't know, so we were just understanding why this cluster is different to this, and then it was clear that, okay, if there's a person, then it belongs to the manta ray image with a person belongs to this cluster, whereas this is manta rays in the deep, it's just blue water and so on. So you're right, it's visual similarity, it could be a combination of pose or co-occurrence of objects, it's combinatorial explosion, right?
And there was like a whole bunch of like works on attribute discovery.
Yes.
Like based on that, you just provide the category label and then they discover other attributes.
Correct. The nice thing, the way we use this actually internally is once we identify this, someone just labels one part of this cluster with some attribute, and it gets closer to this Neil and ever learning kind of thing where there is a human in the loop that is giving some supervision, and you start growing the number of classes. The other one is C3D, which is so the first one is how do you learn representation, where the representation generalizes for various tasks. Second one is how do you do that for video. This is, let me be very honest, this is extremely early work, and this was just the beginning of our way to explore videos, and I honestly feel there is a lot more to do in video, or representation learning in video. So I want you to identify a common theme in all of these videos. So some of the videos were not playing, I don't know, but is there a common theme that you can identify? What is it? Parrot? I know, it's so obvious, right? But if I pass any of these videos to current existing parrot models, none of them will fire. I have, like, it's obvious, right? The challenge is obvious for us. Like, this is, Facebook product groups expect me to tell that this is a parrot, that is a parrot, and so on. But the visual representation of parrot is nowhere close to any of these right now. That's the challenge in video that I face, or our group faces. Okay, so what is a good feature here for video, right? The metrics. Always when you're defining a problem, you need to have some metrics so that you're evaluating yourself. So in our sense, the 4 important things for us when we are trying to understand what is a good feature for video is, first of all, it should be discriminative for your task. So you can use that feature for various distinguishing between this is a parrot versus not, this is sports versus political, and so on. It cannot be megabytes, or each video cannot be represented with megabytes. We have billions of videos. So it has to be extremely compact for the discriminative task. You cannot use hours and hours of compute to extract this representation. So it needs to be very efficient. And finally, the simple the system is, the better. So I know that there is a lot of work around using optical flow to track, and then building orb, SIFT, surf features around each tracklet. That's basically, it's great. It gives you really good accuracy, but it's not simple. So those are all the metrics. So if you just look at video as a sequence of images, then you can actually use the best image model today, and then you can do some sort of pooling or VLAD-like aggregation, and you get the video feature. But what is the problem here? The problem here is you don't explicitly do motion modeling in this space. You do maybe you do implicit motion modeling here, but you have already compressed all of that information into this very high-level feature descriptor. That's a big problem. So how do we train, or how do we design a network that actually does this in a more hierarchical controlled way, where you can combine motion and appearance in a much more constructive way, right? So that's where we were like, obviously, we can start using the 3D convnets as one way to explore this. So you can fuse both spatial and temporal information. But in this, I mean, I think it should be obvious for many people here. What's the difference? In a 2D convolution, you basically have an image and you do spatial convolution alone. In 2D convolution on multiple frames, you basically have RGB. Your filter is actually 3-dimensional as well, but the output you get is basically an image, right? But in a 3D convolution, the input is a volume, the convolution is a volume, and the output is a volume. depending on how much you're aggregating. So that's really, really important. So the most important thing is you're preserving the temporal information in a different space, right? So C3D was our network, and in all honesty, we did not have enough compute, or there was no good video data set. So we ended up building our own data set and then moving to Sports 1 million. And what we did is essentially extend the best architecture that we knew, VGG, to temporal dimension. And that's where the C3D architecture is. It's literally trying to add a temporal dimension to VGG network. And the nice thing is we basically defined multiple losses. So instead of just saying actions or sports, we had multiple loss functions, which is like what is the scene of the video, what are the objects in the video, what are the actions in the video. And the reason for this is simple, because we want the representation to do all of these tasks. And just for sanity check, we visualize the lower level filters. Because these are temporal, you can actually make a nice GIF out of it. The more important thing to see here is it's fast motion, slow motion, vertical, horizontal motion, appearing and disappearing, those kinds of basic constructs along with color filters. So that's what C3D learns. And a good architecture, so the best data set we had was UCF 101. We cannot do architecture, we could not do architecture search on Sports 1 million because of the amount of GPUs required and not getting approval from Mark Zuckerberg. But now we do have that, and we are exploring a lot more here. The two important bits of information that I want you to get out is the observation that we had in spatial in image networks where 3x3 is an atomic convolution is much better than doing 2 3x3 layers convolution back to back with a nonlinearity is better than doing a 5x5. That kind of also seems to hold in the temporal dimension. So we ended up doing 3x3x3 convolutions. And the second one is, let's see, so depth 3. So we can actually also play around with how much in temporal dimension we can see. So it can be a 3x3x3 or 3x3x5 or 7 and so on. Turned out that basically both graphs are suggesting that 3x3x3 atomic convolutions and many such convolutions with nonlinearities gives you the best model that generalizes. So that's what we applied. And the nice thing is when we obviously wanted to beat the benchmark in UCF 101 and Sports 1 million, turned out that it actually helps in various other video data sets like ASLN, which is action similarity labeling, 2 videos, do they belong to the same label or not, and scene classification and egocentric object detection. So you just literally take the feature that you have learned. Of all the works in the representation learning, if you see, we take the representation. We don't fine-tune it for the task. We want to learn a representation that is valid for various tasks, right? So even here, we take the representation learned on Sports 1 million and apply it on these other data sets without fine-tuning on the data sets. And we were able to do better than the existing accuracies. I think these numbers are old. There probably are LSTMs on top of C3D now that outperform. So this, like I said, this is just the beginning. Okay. The third one was discriminative. Remember, discriminative, compact, and so on and so forth. So in compact, we just did a PCA on the feature descriptor, and with 10 numbers, we were able to get to 50% accuracy on UCF 101, which is 101 classes. So it is actually extremely compact. So if you want to lose accuracy and you just save 10 numbers for each clip, you will still be able to get a reasonably good accurate prediction system. So it's really efficient. If you take the best model out there right now, IDT, which is the intensive dense trajectory, or I don't remember what I stands for, incremental dense trajectory, which is much slower because of how it is. It's not GPU friendly and so on, whereas C3D is much faster. And yeah, you do t-SNE and see how this visual embedding is for various classes on UCF 101. And you can clearly see that if you just use the image representation, it's not as good. But if you remember, both these data sets are not trained on UCF 101. Both these features are trained. One is trained on ImageNet, and the other one is Sports 1 million. There is an inherent bias here because Sports 1 million might be closer to UCF 101. So in some sense, this is a little bit of an unfair comparison. But the last one, as I said, is we really, really want to learn representations in an unsupervised way, but we need to start somewhere. It always feel like taking a smaller problem, making progress, and then incrementally improving is much, much better than taking the grander problem and failing at it after 2 years. So, so unsupervised learning of edges. So basically, the idea here was if you look at the most promising works in the beginning of computer vision, Harris Corner or edge detectors. Those were the fundamental features that were on top of which we built and had handcrafted features and so on. So can we start looking at these fundamental problems again with deep networks and learn them in an unsupervised way where there is no supervision? That's the higher order bit, what we were trying to solve here. And Yin Lee is the person who, from Georgia Tech, he was a PhD student. He did a fantastic job here. So I want you to see this video. Right now, probably it's not clear as to what is the foreground and what is background. But in a very quickly, you will know what is foreground and what is background. Okay. So this is a motivational video. It's like every time you want to have some motivation, right? And if you look at the optical flow of that video, you'll basically get this. If I can play it. Oh man, you're missing out on the. There you go. So you get like really vivid contour, like edges of the object, of the foreground. It's like, you can use this information, right? It's very clear intuitively that we should be able to use this information to understand what is an edge, what is a foreground, and what is background. That's the motivation for this. So can we learn edges from video? No supervision. Looking at the video, like looking at millions of videos of the world, can we build an edge detector that beats the state of the art or comes close to the state of the art, which is fully supervised? So apply it on 2 frames. So you can do optical flow. You can use any off-the-shelf optical flow dense correspondence. And you get, there are motion discontinuities. And when there is a motion discontinuity, there is an edge. And then there's also image edges. Now the question is, obviously, this is a universal set. This is a subset, right? So what we have as supervision when we look at the video is just these. The question is, we are trying to use these to learn this, which will always be subpar compared to actually annotating the edges. There's no doubt about it, but we want to try, right? So we take frame pairs, we do optical flow. Once we have optical flow, we take the best edge detector that is appearance-based, apply it on that, and you apply some heuristics. The heuristics are in the paper. Don't want to get into the details. You get some positives. And the motion edges are obviously always a subset of the actual image edges. But if you take confident motion edges as positives and do that for millions of videos, hopefully we have removed certain biases and we will be able to learn a good, think of this as weak supervision in some sense, where video supervision basically. So video is giving you the supervisory information. Edges are sparse, so you can see what kind of edges we pick as ground truth. So this is ground truth for the network to learn for doing edge detection. And we basically compute flow, and it's an iterative manner. We update the flow, we get the edges, and we improve the edges and so on. Look at millions of such videos, and we can then ask these questions. Has my model learned enough to get image edges? And turns out that we can actually do that. So this is the ground truth, and these are the outputs that we get purely from a network that is trained to predict edges on on the example that I showed, where the edges are optical flow edges on millions of videos. So that's pretty much what I had on the representation learning aspect. I'm going to quickly end with a few open questions for you guys and for myself as well. So given how much progress we have made over the past 3 or 4 years, we always ask ourselves, are we there yet? And I don't know how many of you know about the Google's photo tagging fiasco, basically where they labeled black people as gorillas. So this is an extremely challenging problem, right? And when we were shipping automatic alt text, this was one of the most important things that we were like, what are the misclassifications across the concepts? So these were, we actually did not ship the tag animal purely because of this. There was no way for us to get 100% accuracy on animal. So this was actually, if someone wore a costume, which is it's a genuine question. It's like, should we say it's a tiger or not? So obviously, we want the system to say a tiger costume a human is wearing or something like that. And then it did not have enough negative examples of people swimming for sharks or for dolphins. You can see that arm is considered as a fin or something like that. So what I'm trying to say here is the loss functions, the misclassifications are, there is a completely different loss function where the weight of misclassification for one class is different to another class. Misclassifying a dog and a cat is totally fine, but an animal and a human, no. Other things, if you push the existing segmentation algorithms and look at low scoring, low confidence segmentation regions, you actually get these refrigerator and mouse on the ceiling and so on. And this is where we as scientists then say, oh, no, we'll start using context. But if you look at some of these deep learning models, there was one interesting thing that we were trying to do where we took a person wearing a suit and we removed the tie, actually inpainted the tie and send it to ask the deep network, and it actually classifies it with a reasonable probability on a tie, because most of the examples that the deep network has seen with suits are people with ties. So now we need to be conscious and say, oh, okay, I also need to show you people with suits without tie. So when we start dealing with millions of examples and this high capacity models, these kind of context things are implicitly built into the model. So it's really, really important to interpret these models and understand how to build our data sets so that we can counter these. So we are definitely not there yet. That's what my message was. So to conclude, it's really, really crucial at Facebook that we have the best models in computer vision. We have unique challenges in terms of variety and size, and we are doing not only short-term shipping stuff, but also mid and long-term research, asking fundamental questions on how to build universal models, universal representations, and so on. So yeah, that's our goal, provide superpowers to humans with the help of AI, and in this particular case, with the help of computer vision. Thank you.